All right. Okay, so we have dealt with the beams. Now it's time for you to see something else. Now this is a frame now, but this is a simple frame because if you go to see my slide, this is what we call non-sideway frame, okay? Non-sideway. Now, when do we have sideway frames and when do we have a non-sideway frame? Now, generally, if you can recall, I drew one frame earlier today. Okay, this one would definitely sway simply because if you look at the members here, there is no lateral restraint. So when we have the lateral load, it would just go to the side, and we call that side sway. Now, I can also have the side sway frame even though I don't have the lateral load. Okay, that's the same frame. When I have the non-symmetric load, like this, just a portion of this will, cause your frame to move a little bit awkwardly, and therefore chances are it's just going to go to the side as well. So this one will sway. You will have non-sideway frame in one of the two cases. Okay, so let's erase this. Say non-sideway. One, when you have a symmetric frame and symmetric loading condition. Okay, so let's say the same I, same length, and then the loading happens to be symmetric. So symmetric structure and symmetric loading condition. There will be no sideway because your frame will just come down like this. Okay. Or second, when you have, let's say, same frame, but there is some kind of lateral restraint. So in this case, you have lateral restraint. Okay, you have the reaction here, so it will not move. Okay, so one of the two cases, you have the non-sideway frame and you don't have to solve for the delta. Okay, but if this is not the case, you will have it. So let's come back here. This frame, you have the lateral restraint here. So it will not move sideways. That means you can just go on and tackle this right away. So let me try to give it a name, okay? This one is A, that one is B, that one is C, and this one is D. Now the only major difference from all those beams that we have done before is that, at B is joined by three members. So when you write your sigma MB equal to 0, you just need to include MBA plus MBC and then plus MBD. That will be equal to 0. That's it. The rest is pretty much the same. So we can just get on with it, right? And let's say now C and D are fixed. So you know that your zeta C and zeta D are both 0. So when you identify your unknowns, let's say two unknowns, that is zeta A and zeta B. Now, can we eliminate zeta A because isn't this a simple n? Well, you can look at your structure, and if you can say that, okay, MA is 0, for sure. If that's the case, you can always eliminate zeta A. Yes, but remember, you eliminate it, it doesn't mean that it is 0. Okay. Now, before we go on and use that extra equation, let me carry on and show you that if you don't want to use that equation, you can always, wrap it up or try to solve that equation before you create your moment equation. Okay. So let's move on to the next step. 1. Relative stiffness. Okay, so we have KAB, that is 2I over 3. KBC, it's 3I over 4, and then KBD, that's 2I over 2. Okay, so I can say I'm going to use K equal to I over 6. Now my KAB, multiply everything by 6, so it becomes 4K. This multiplied by 6, it becomes 4.5K. This multiplied by 6, it becomes just 6, right? And now it's a bit tricky for the fixed moment because we have so many loads, so got to do some calculation, right? FEMAB, you need to use the formula. That's minus PAB squared, yep, over L squared. That is minus the load is 4 tons. Your A is 1. Your B is 2. And your L is 3. It's getting a bit long. This is minus 16 over 9 ton meter. FEMBA. Remember, when you have the load not in the middle, they're not equal, right? So this is plus now because it's BA, and then it becomes A square B over L square. So that is 4. 1 square. Just writing it so that you can see the complete picture. Multiply by 2 divided by 3 square. So this is equal to 89 ton meter. And then piece of cake, FEMBC is minus WL square over 12. So that is minus 1.5. That's 4, right? So 4 square over 12. This is equal to minus 2 ton meter. And if you're lazy, you can say this is equal to minus FEMCB. Right, so that's it. Now if you are not going to use the modified equation, you can write your MAB that is equal to 2E 4K 2 zeta A plus zeta B. And I'm lazy now, so I'm not going to write the sine term because we know it's 0, right? That is minus 16.9. And then MBA 2E 4K 2 zeta B plus zeta A plus 8/9 MBC 2E BC, we have like 4.5K, right? Okay. 2 zeta B. Zeta C is 0, so I'm lazy. I'm not going to write it anymore. That's minus 2. MCB 2E 4.5K zeta B plus 2. And then you have MBD. That's pretty much like a column, you know. So it's 2E 6K. And we have 2 zeta B. No fixed moment. Okay. Now, if you don't, okay, forgot to write that this is SD equation. Now, if you are lazy, you can, of course, take care of this. You see, you can eliminate this, but in the end, it will give you MBA just like that equation, all right, which is equal to, oh, again, what's behind this one? One moment, please. Three EK, 4K, zeta B, MBA, right? Plus 8/9 minus 16/9. Okay. Well, if you don't want to use this one, if you want to write your simple equations, you can start off by solving this first. And when you solve this, it means that you no longer have to write your sigma MA equal to 0. Oh. Okay. But if you still want to do it, nobody's going to kill you, but you're going to kill yourself if you make a mistake. That's all. Okay. And let's say if you still want to do it, you will have your AB equal to 0. Seems a bit silly, really. So there you have it. You have that equation arranged So this is 16 EK zeta A plus 8 EK zeta B minus 16 over 9 equal to 0. And then MBA. Oops, I'm sorry. It's my mistake. Sigma MB equal to 0, which is MBA plus MBC plus MBD equal to 0. Okay, but you know, if you begin your equation like this, you must be careful, because if you are solving this one, if you have zeta A and zeta B, your MBA here must be this one. Okay, so that becomes 8 EK zeta A plus 58 EK zeta B minus 10/9 equal to 0. Okay, or if you use this one, I didn't have it, but we can do it together. That's 12, right? And then how much is that? That's 18. That's 24. 24, 18. It's 42, right? 42 plus 12. It's 56. They're not equal. Somewhat, okay. Maybe you can check me later. 56 EK zeta B, and then easy. Let me it's 18. Yeah. It's, 42, 50. Huh? So 54, right? That's 58. 54, and then you have this. So that's 24 over 9 plus 2. Just one equation. If you use the modification, you have only one equation. And then you solve, you get zeta B. But if you don't, if you refuse to do it, you need to solve two equations, which is this and this. In the end, if you solve two equations, you get EK zeta A equal to 0.10905, and then EK zeta B is equal to 0.00412. But then again, you feel a little bit maybe strange, because you get this value, you bring this back to this equation with zeta B, knowing that MAB is going to be 0. So it's a bit, you know, unnecessary to do it. And because if you use the modification with zeta B alone, you already get you get MBA, and you get MBC and MBD right away, because it's only a function of zeta B. So it's absolutely unnecessary to solve for zeta A. Okay, and let me remind you again that it's not 0. Okay, and once you do this, you can go back and put everything back into your corresponding slope deflection equation to get n moments. Okay, and MAB is of course 0. MBA is 1.83 ton-meter. Let me erase that. It looks ugly, maybe confusing. then make it better. Okay, MBC is minus 1.93 ton meter. MBD, you see, sorry. MBD is only 0.1 ton meter. So you see, such a small contribution from the column. MCB is 2.04 ton meter. And MDB almost 0. Because if you go back and look at the structure, if you don't have a sway problem, this becomes almost like, you know, a typical continuous beam problem because it's non-sideway. So the existence of BD almost counts for nothing. You might as well analyze this structure by doing this. Right? You almost get the same result because of that. So now let's go back here and oops. Oh, does that a lot. Try to finish this off. Okay, and 6 is reactions. Okay, so again, remember that all your numbers at from the equation means that clockwise positive. So your MBA is positive, so that's clockwise of 1.83, and then you have the point load here, 4 tons. Okay, remember that MAB is 0, and the second piece, that's BC, I suppose. You have a negative value here, so it's counterclockwise of 1.93, and CB is positive, so you have clockwise moment and then with the uniform load. And the last one is the column, which almost nothing on it. MBD is clockwise, and then MDB is also clockwise. So it's like this. So from this on, you know, you can just use your equilibrium to solve for the values. But I can give the number straight away, just in case you want it. Let's change the color a little bit so that life becomes slightly more colorful. Using the simple equilibrium, you get 2.06. And here is 1.94. Here is 2.97. And here is 3.03, and everything is going clockwise in the column. So you have, you know, a couple here with the value of so tiny, 0.75. You know what this number is? This is the shear in your column. So you see, if you don't have a sideway problem, this problem sort of shows you that you don't need to include your columns in the analysis of your continuous beam at all. Okay, in a way. So from this, I suppose you can go on and complete your shear force and bending moment diagram. So that's it. For me, is there any question? Folks, that's it. One, two, three question. Crystal clear, right? Hello? Hello?
For the
Huh?
2.06 is from the find the reaction, right?
Yes, that's correct. By using your equilibrium. Okay? It's a cake, don't you think? Couldn't find anything easier than this. So you see, one clear character is that this is, say, methodical. That's the word. Everything can be done step by step by using the procedure. So that is why some of you may find yourself doing this better than the force method from the Jurassic world. You see what I'm saying, right? Nobody uses that method anymore. And perhaps you may find yourself not using this because you use computers, but it's a quick method nonetheless. And sometimes it is quicker than computers. And we are still with the slope deflection method now. And after this method, it's another method that it's nothing more than, you know, the mathematical solution for slope deflection. And you may find that method is even more quicker than slope deflection and much quicker than you try to use a computer right away. You know, many times. It just can you can analyze continuous beams, say, within minutes. And especially you find that sometimes you don't really need the exact number of moment and shear. You can just use these methods to approximate what's going on with your structure very, very quickly. Right? Is there any other question? Hello? So if there isn't anything, I'm gonna stop the share and go back to the main screen, and I will stop the recording as well.